They said it was impossible. No one had ever changed a fighter plane engine in under 2 hours, let alone 5 minutes. The manual said it required a full maintenance crew, proper tools, and at least 120 minutes of careful work. But when Technical Sergeant Jake "Wrench" Thompson heard the radio crackle with desperate voices on March 15, 1944, he didn't have 2 hours. He had 5 minutes before an entire squadron of American P-51 Mustangs would be caught on the ground by incoming German fighters, sitting ducks with nowhere to run. Jake looked at the smoking engine of Lieutenant Bobby "Ace" Morrison's Mustang, then at the perfectly good engine sitting in a crate 20 yards away, then at his watch. 4 minutes and 50 seconds. The mathematics of survival had never been more brutal or more clear. Every second Jake saved meant American pilots would live. Every second he wasted meant they would die. What happened next would defy every engineering principle, violate every safety protocol, and prove that sometimes the impossible becomes inevitable when failure means watching your friends burn alive on a runway while enemy fighters dive out of the sun. If stories like this fascinate you, make sure to hit that subscribe button. These accounts reveal how American ingenuity and sheer determination achieved what experts said couldn't be done. The morning sun cast long shadows across Debden Airfield in England, home to the 4th Fighter Group and some of the most experienced P-51 Mustang pilots in the European theater. The air was crisp and clear, perfect flying weather that meant both American and German fighters would be active over the skies of occupied Europe. Technical Sergeant Jake Thompson, 28 years old from Detroit, Michigan, moved between the parked Mustangs with the practiced efficiency of someone who understood every bolt, wire, and moving part of the aircraft he maintained. Jake had been working on engines since he was 12 years old, starting with farm tractors in rural Michigan and progressing through auto repair shops before joining the Army Air Forces in 1942. The P-51D Mustang was a masterpiece of American engineering, powered by a Packard V1650-7 engine that produced 1,695 horsepower and could push the fighter to speeds over 440 miles per hour. But for all its sophistication, the Mustang was still a machine, and machines broke down at the worst possible moments. Jake's responsibility was keeping 12 Mustangs in perfect flying condition, a job that required not just mechanical skill but an intuitive understanding of how engines behaved under the stress of combat flying. He could diagnose problems by listening to subtle changes in engine sound, feel potential failures through vibrations in the airframe, and predict maintenance needs based on pilot reports and flight hours. This morning, Jake was focused on Lieutenant Morrison's Mustang, which had returned from yesterday's escort mission with what the pilot described as funny noises and rough running. Jake's preliminary inspection had revealed oil contamination in the engine, suggesting internal damage that would require major repair work. Under normal circumstances, Morrison's aircraft would be grounded for several days while Jake and his crew performed a complete engine overhaul. But these weren't normal circumstances. Intelligence reports indicated that the Luftwaffe was planning a major offensive against Allied bomber formations, and every available fighter would be needed to protect the bombers and their crews. The radio in the maintenance hangar crackled to life with an urgent message that would transform Jake's routine maintenance work into a desperate race against time. The emergency that changed everything. All fighter squadrons, scramble immediately. The voice belonged to Major Robert Johnson, the 4th Fighter Group's operations officer, and the urgency in his tone made every pilot and ground crew member stop what they were doing and listen. Large formation of German fighters approaching bomber stream. All available aircraft get airborne now. Jake watched as pilots sprinted toward their aircraft, pulling on flight gear as they ran. Engines roared to life across the airfield as Mustangs prepared for immediate takeoff. But Lieutenant Morrison stood beside his aircraft looking desperate and frustrated. His Mustang's engine was partially disassembled for the maintenance work Jake had been performing. How long to get her running? Morrison shouted over the noise of starting engines. Jake looked at the Mustang's exposed engine bay, the removed components scattered around his work area, and the replacement parts that would be needed to complete the repair. Under normal circumstances, reassembling the engine would take 2 to 3 hours of careful work. 2 hours minimum, Jake shouted back. Morrison's face went pale. The squadron's taking off in 10 minutes. If I'm not with them, they'll be one fighter short against whatever the Germans are throwing at us. Jake understood the implications immediately. Fighter squadrons operated as carefully coordinated teams, with each pilot responsible for protecting his wingman and section leader. One missing aircraft could disrupt the entire formation's defensive capabilities and leave other pilots vulnerable to attack. But 2 hours was 2 hours. There was no way to safely reassemble a fighter engine in less time without risking catastrophic failure that could kill the pilot and destroy a valuable aircraft. Then Jake remembered something that changed everything. In the corner of the maintenance hangar sat a shipping crate containing a brand new Packard V1650-7 engine, delivered just 2 days earlier as a replacement for another aircraft that had been damaged beyond repair. The engine was completely assembled, tested, and ready for installation. The crazy idea that occurred to Jake violated every maintenance regulation and engineering principle he had ever learned. Instead of repairing Morrison's damaged engine, he could remove it entirely and install the new engine from the crate. But engine replacements normally took 4 to 6 hours with a full crew of specialists using proper lifting equipment and precision tools. Jake looked at his watch. The squadron was scheduled to take off in 8 minutes. Even if he started immediately, there was no way to complete an engine change in that time. Unless he tried something that had never been attempted before. The 5-minute impossibility. Jake made his decision in the time it took his heart to beat twice. Morrison. Get in the cockpit and start your pre-flight checks. This bird's going to fly. Morrison stared at Jake as if the mechanic had lost his mind. You said 2 hours. I lied, Jake shouted, already sprinting toward the shipping crate containing the new engine. 5 minutes. Get ready to start engines. What Jake was proposing violated every principle of aircraft maintenance. Fighter engines were precision-built machines weighing over 1,400 pounds, with hundreds of connections for fuel, oil, electrical, and control systems. Installation required careful alignment, torque specifications, and systematic testing to ensure safe operation. But Jake had advantages that the manual writers hadn't considered. He had been working on Morrison's specific aircraft for 8 months and knew every quirk and characteristic of its systems. He had memorized the location of every bolt, connection, and mounting point. Most importantly, he had an intuitive understanding of how engines and airframes worked together that went beyond textbook knowledge. Jake's plan was brilliant in its simplicity and terrifying in its audacity. Instead of following the standard procedure of removing the old engine first, then installing the new one, he would perform both operations simultaneously. While the damaged engine was being disconnected, the new engine would be positioned and aligned for immediate installation. The technique required perfect coordination, split-second timing, and a level of mechanical skill that few people possessed. One mistake in alignment or connection could destroy both engines and potentially the aircraft. But Jake was betting his reputation, Morrison's life, and the success of the mission on his ability to achieve the impossible. Tommy. Eddie. Get over here now. Jake yelled to his 2 assistant mechanics, Corporal Tommy Martinez from Texas and Private Eddie O'Brien from Boston. Both men had been working with Jake for months and understood his methods, but neither had ever attempted anything like what Jake was proposing. Jake quickly outlined his plan while pointing to specific components and connections. Martinez would handle the electrical and control connections while O'Brien managed fuel and oil lines. Jake would position and align the engines while coordinating the overall sequence. This is crazy, O'Brien muttered, but he was already moving toward the aircraft with a tool kit in his hands. Crazy is relative, Jake replied, using a portable crane to lift the new engine from its crate. Crazy is watching Morrison get shot down because we followed the manual instead of using our brains. The radio crackled again with increasing urgency. All aircraft, engines start in 3 minutes. Mission is go in 5 minutes. Jake looked at his watch. 4 minutes and 30 seconds to achieve the impossible. The precision ballet of controlled chaos. What happened next resembled a perfectly choreographed dance performed at triple speed by people who trusted each other completely. Jake positioned the portable crane to support the new engine while simultaneously disconnecting the damaged engine from its mounting points. Martinez worked with surgical precision on electrical connections, his hands moving in practiced sequences he had performed hundreds of times but never under such pressure. Each wire had to be disconnected from the old engine and immediately reconnected to the new one without delay or error. O'Brien handled the fuel and oil systems with similar expertise, bleeding pressure from lines before disconnection and ensuring proper sealing when connecting to the new engine. Fuel contamination or air bubbles in the system could cause engine failure during flight, potentially killing Morrison over enemy territory. Jake coordinated the entire operation while performing the most challenging task, aligning and installing the new engine in precisely the correct position. The engine had to mate perfectly with transmission connections, control linkages, and structural mounting points. A misalignment of even a fraction of an inch could prevent proper operation or cause catastrophic failure. The work required strength, precision, and an intuitive understanding of mechanical systems that went beyond formal training. Jake could feel through his hands when connections were properly seated, when alignment was correct, and when systems were ready for operation. Electrical connections complete. Martinez shouted. Fuel and oil systems connected. O'Brien reported. Jake was tightening the final engine mount bolts when the radio announced, "All engines start now." Around the airfield, Mustang engines roared to life as pilots began their takeoff sequence. Morrison sat in his cockpit, hands on the controls, watching Jake work with desperate intensity. "Try it now," Jake yelled, stepping back from the aircraft. Morrison engaged the starter. The new engine turned over once, twice, then caught with a healthy roar that sounded perfect to Jake's experienced ear. Oil pressure came up normally, engine temperature stayed in the green range, and all control responses checked normal. Jake had achieved the impossible. In exactly 4 minutes and 47 seconds, he had removed a damaged engine and installed a replacement that was running perfectly. But the real test was still to come. The takeoff that proved everything. Lieutenant Morrison advanced the throttle and his Mustang began rolling toward the runway, joining the formation of fighters preparing for takeoff. Jake watched from the flight line, knowing that the next few minutes would determine whether his unprecedented engine change had been a brilliant success or a catastrophic mistake. The Mustang's new engine sounded strong and steady as Morrison taxied into position. But the real test would come during takeoff and climb, when the engine would be subjected to maximum power settings and stress loads that could reveal any problems with Jake's installation. Morrison lined up on the runway and pushed the throttle forward. The Mustang accelerated smoothly, the new engine developing full power without hesitation or irregularity. Jake held his breath as the fighter lifted off and began climbing, watching for any signs of trouble that would force Morrison to abort the mission. But the Mustang climbed strongly and smoothly, joining the formation of other fighters as they headed toward their rendezvous with the bomber stream. Jake's engine change had worked perfectly. The radio crackled with Morrison's voice, "Wrench, this is ace. Engine running like a dream. You just saved my bacon and maybe a lot of other people's too. Thanks, partner." Jake felt a mixture of relief, pride, and exhaustion as he watched the fighters disappear into the distance. He had achieved something that every expert said was impossible, and he had done it under the worst possible conditions with lives depending on his success. But Jake's innovation was about to have consequences that extended far beyond one successful takeoff. The technique that revolutionized field maintenance. Word of Jake's 5-minute engine change spread through the 8th Air Force maintenance community with remarkable speed. Other mechanics initially refused to believe the reports, insisting that no one could safely replace a fighter engine in less than 5 minutes. But when Jake was asked to demonstrate his technique for other maintenance crews, the results spoke for themselves. Using the same methods he had developed during Morrison's emergency, Jake successfully performed engine changes in times that ranged from 3.5 to 6 minutes, depending on the specific circumstances and aircraft condition. The key to Jake's success was his systematic approach to engine installation that eliminated unnecessary steps and combined multiple operations that were normally performed sequentially. By preparing all connections and alignments before removing the old engine, Jake could install the replacement with minimal delay and maximum efficiency. More importantly, Jake's technique maintained all necessary safety standards while dramatically reducing installation time. His engines operated as reliably as those installed using conventional methods, proving that speed and safety were not mutually exclusive when the work was performed by skilled technicians. Colonel William Kepner, commanding officer of the 8th Fighter Command, observed one of Jake's demonstrations and immediately ordered the technique to be taught to maintenance crews throughout the fighter groups. The ability to perform rapid engine changes could keep more aircraft operational and available for combat missions. Jake was temporarily assigned to the 8th Air Force Technical Training Command, where he developed standardized procedures for rapid engine replacement that could be used by mechanics with varying levels of experience. His methods were incorporated into official maintenance manuals and became standard practice for emergency situations. The impact on combat operations was significant. Fighter squadrons that had previously lost aircraft to extended maintenance downtime found they could keep more planes operational and available for missions. The technique proved particularly valuable during periods of intensive combat operations when aircraft availability was critical for mission success. But perhaps the most important impact was on morale. Pilots who had previously worried about being grounded by mechanical problems gained confidence that their aircraft would be repaired quickly and returned to service. This confidence translated into more aggressive flying and better combat performance. Jake's innovation demonstrated that conventional wisdom about maintenance procedures was not always correct, and that experienced mechanics could achieve remarkable results when they understood their equipment thoroughly and were willing to challenge established methods. The combat test that validated innovation. The true test of Jake's rapid engine change technique came during the massive air battles of Big Week in February 1944, when the 8th Air Force launched intensive bombing campaigns against German aircraft production facilities. The operations required every available fighter to escort the bombers and protect them from Luftwaffe interceptors. During this period, Jake's squadron faced unprecedented maintenance challenges. Aircraft returned from missions with battle damage, mechanical problems, and wear-related issues that would normally require extended maintenance periods. Using conventional repair methods, the squadron would have been able to field only half its aircraft for subsequent missions. But Jake's rapid engine change techniques allowed the maintenance crews to keep nearly all aircraft operational throughout the campaign. Engines damaged by combat or mechanical failure were replaced in minutes rather than hours, allowing pilots to fly multiple missions per day when needed. The results were dramatic. Jake's squadron achieved one of the highest aircraft availability rates in the 8th Air Force, enabling them to provide continuous escort coverage for bomber formations and contribute significantly to the success of the strategic bombing campaign. Lieutenant Morrison, whose aircraft had been the first to benefit from Jake's 5-minute engine change, became one of the squadron's most successful pilots during this period. Flying the Mustang with Jake's installed engine, Morrison shot down 4 German fighters and helped protect dozens of American bombers from enemy attack. The success of Jake's techniques was noted by higher command levels and contributed to the decision to expand their use throughout American fighter units in Europe. By late 1944, Jake's methods were being used by maintenance crews across the European theater, improving aircraft availability and combat effectiveness. But the impact extended beyond immediate military applications. Jake's approach to problem-solving and his willingness to challenge conventional procedures inspired other mechanics and technicians to develop their own innovations for improving maintenance efficiency and aircraft reliability. The recognition that field conditions required different approaches than depot-level maintenance led to significant changes in how the Army Air Forces trained and equipped their maintenance personnel. Jake's success demonstrated that experienced mechanics with proper tools and techniques could achieve results that exceeded peacetime standards for quality and efficiency. Most importantly, Jake's story illustrated that innovation often comes from practitioners who understand their equipment intimately and are willing to take calculated risks to achieve important objectives. His 5-minute engine change had saved not just one pilot and one aircraft, but had contributed to improving the combat effectiveness of American air power in Europe. The legacy of mechanical genius. Jake Thompson's innovations continued to influence aircraft maintenance practices long after his initial 5-minute engine change. His techniques were studied, refined, and adapted for use with different aircraft types and operational conditions throughout the war. The fundamental principles Jake had established, thorough preparation, systematic approach, and elimination of unnecessary procedures, became standard elements of rapid maintenance techniques used by the Army Air Forces and later the U.S. Air Force. During the final year of the war in Europe, Jake was promoted to Master Sergeant and assigned to develop advanced maintenance procedures for the new jet aircraft that were beginning to enter service. His experience with rapid engine changes proved invaluable in creating maintenance protocols for aircraft that operated under even more demanding conditions than propeller-driven fighters. Jake's influence extended beyond engine maintenance to other aspects of aircraft repair and modification. His systematic approach to problem-solving and his emphasis on efficiency without compromising safety became models for maintenance innovations throughout the military aviation community. Lieutenant Morrison continued flying combat missions with the engine Jake had installed and eventually completed his tour with a record of 8 confirmed victories against German aircraft. Morrison credited Jake's maintenance work with enabling him to fly missions that contributed directly to Allied victory in Europe. The relationship between Morrison and Jake exemplified the crucial partnership between pilots and maintenance personnel that was essential for combat effectiveness. Morrison's success in aerial combat depended entirely on Jake's ability to keep his aircraft in perfect mechanical condition, while Jake's satisfaction came from knowing that his work enabled pilots to complete their missions and return safely. After the war, Jake returned to Detroit where he used his military experience to establish an aircraft maintenance business that served civilian and commercial aviation customers. His reputation for rapid, reliable repairs made his company one of the most successful in the region. Jake rarely spoke publicly about his wartime innovations, preferring to let his work speak for itself. But the techniques he developed continued to influence aircraft maintenance practices for decades after the war ended, and his approach to problem-solving became a model for mechanics and technicians in many fields. The broader lessons Jake's story illustrated, that expertise combined with innovative thinking could overcome seemingly impossible challenges, proved relevant far beyond aircraft maintenance and influenced American approaches to technological problems in many areas. Most importantly, Jake Thompson had demonstrated that individual initiative and technical competence could have effects that extended far beyond immediate circumstances. His 5-minute engine change had not only saved one pilot and one aircraft, but had contributed to innovations that improved the effectiveness of American air power throughout World War II. The human impact of technical excellence. Behind the statistics and technical achievements of Jake's innovations were human stories that illustrated the profound impact of individual competence and dedication. The pilots who flew aircraft maintained by Jake and his trained crews knew they could depend on their aircraft to perform reliably under the most demanding conditions. This confidence was crucial for combat effectiveness. Pilots who trusted their equipment could focus entirely on mission accomplishment and tactical considerations without worrying about mechanical reliability. They could push their aircraft to performance limits when necessary, knowing that proper maintenance had prepared the aircraft for maximum stress. The psychological impact was equally important. Knowing that expert mechanics like Jake were responsible for aircraft maintenance gave pilots confidence that extended beyond mechanical considerations to overall mission planning and execution. Pilots flew more aggressively and took calculated risks that contributed to mission success because they trusted that their aircraft would perform as intended. Jake's relationship with the pilots he supported was characterized by mutual respect and professional dedication. Pilots appreciated Jake's commitment to keeping their aircraft in perfect condition, while Jake took personal pride in knowing that his work contributed directly to pilot survival and mission success. This partnership between pilots and mechanics represented one of the crucial human relationships that enabled American air power to achieve decisive results in World War II. The technical competence of ground crews was just as important as pilots' skill in determining combat effectiveness. Jake's innovations also had significant impact on other maintenance personnel who learned his techniques and adapted them for their own use. Young mechanics who worked with Jake gained experience and confidence that served them throughout their military careers and in civilian employment after the war. The training programs Jake developed influenced thousands of mechanics and technicians who carried his methods to other units and other conflicts. His emphasis on thorough understanding of equipment and systematic approaches to problem-solving became standard elements of military technical training. Perhaps most importantly, Jake's story demonstrated that technical excellence and human compassion were not contradictory but complementary. His innovations were motivated not by abstract engineering challenges but by concern for the pilots who depended on his work for their lives and safety. The knowledge that good maintenance work could mean the difference between life and death for pilots gave Jake and his crews a sense of purpose and responsibility that elevated their technical work to a higher level of professional dedication. The innovation that transcended war. As World War II ended and the aviation industry transitioned to peacetime operations, Jake Thompson's maintenance innovations found new applications in commercial and civilian aviation. The rapid repair techniques he had developed for military aircraft proved equally valuable for airlines and aircraft operators who needed to minimize maintenance downtime and maximize aircraft utilization. The principles Jake had established, systematic preparation, efficient procedures, and uncompromising safety standards, became standard practices in the growing commercial aviation industry. His influence could be seen in maintenance procedures developed by major airlines and aircraft manufacturers throughout the 1950s and 1960s. Jake's emphasis on thorough training and technical competence for maintenance personnel influenced the development of civilian aircraft mechanic certification programs. The standards he had established for military mechanics became models for civilian training programs that produced the skilled technicians needed to support the rapid growth of commercial aviation. The jet age presented new challenges that required adaptations of Jake's techniques for aircraft with different engines and systems. But the fundamental approaches he had pioneered, understanding equipment thoroughly, preparing systematically, and executing efficiently, remained relevant for the most advanced aircraft. Jake's story also illustrated broader themes about American innovation and problem-solving that extended far beyond aviation. His willingness to challenge conventional procedures and his confidence in developing better methods reflected characteristics that contributed to American technological leadership in many fields. The combination of technical competence, innovative thinking, and practical experience that Jake represented became a model for American approaches to technological challenges throughout the post-war period. His success demonstrated that individual expertise and initiative could achieve results that exceeded what institutional procedures and conventional wisdom said was possible. Most importantly, Jake's legacy was a reminder that innovation often comes from practitioners who understand their tools and challenges intimately, rather than from theoretical experts who may lack practical experience. His 5-minute engine change had emerged from deep understanding of aircraft systems combined with the pressure of real-world circumstances that demanded immediate solutions. The enduring lesson of practical innovation. The broader significance of Jake Thompson's story extends beyond aircraft maintenance to fundamental questions about innovation, expertise, and the relationship between theoretical knowledge and practical application. Jake had demonstrated that deep understanding of equipment and systems, combined with willingness to challenge conventional procedures, could achieve results that seemed impossible according to established standards. His approach required a particular kind of confidence, the confidence that comes from thorough knowledge and extensive experience rather than from following established procedures. Jake had been willing to risk his reputation and career on techniques that violated standard practices because he understood his equipment well enough to know what was truly necessary and what was merely conventional. This kind of practical innovation became increasingly important as technology grew more complex and operational demands more severe. The principles Jake had pioneered, systematic analysis, efficient execution, and continuous improvement based on results, proved essential for success in rapidly evolving technological environments. Jake's legacy was also a reminder that innovation often requires the courage to attempt solutions that experts say are impossible. His 5-minute engine change had succeeded not because it was theoretically sound according to established engineering principles, but because it was practically effective under real-world conditions. The relationship between theoretical knowledge and practical application that Jake's story illustrated became a central theme in American technological development. The most successful innovations often came from people who combined formal training with extensive hands-on experience and were willing to challenge conventional wisdom when circumstances demanded better solutions. Perhaps most importantly, Jake Thompson's story demonstrated that individual competence and initiative could have effects that extended far beyond immediate circumstances. His innovations had not only solved an urgent problem for one pilot and one aircraft, but had contributed to improving the effectiveness of American air power throughout World War II. So here's the question Jake's story poses: in your own field, what conventional procedures are you following that might not be the most efficient or effective approaches? What innovations might be possible if you combine deep understanding of your tools and challenges with willingness to challenge established methods? And do you have the confidence that comes from real expertise to attempt solutions that others say are impossible? Jake Thompson proved that sometimes the most important breakthroughs come not from following the manual, but from understanding your equipment so thoroughly that you know when the manual is wrong and having the courage to do what actually works rather than what you're supposed to do.